Thank you, Dean. We've got to wait just a minute for, despite all the technology, we've still got to switch from Mac to PC. And that's, isn't that an interesting part of the world that for all the advances we've made, we still have a Mac world and a PC world? And I operate in the PC world, and I guess UCSB operates at least part in the Mac world. I have two daughters who are both involved in the arts, and they can't believe that I use PCs. You probably all see that problem. Of course, they have iPods and all of the other stuff that I don't have. Anyway, what we want to talk to you about today is really an interesting enabler for some of the things that the Dean just mentioned. We think about energy efficiency, and we think about greenhouse gases, and we think about inconvenient truths. I mean, imagine that a politician won the Nobel Prize. You either think that this is a real sign of human advancement or that the Nobel Prize has gone to hell, and you can really look at it either way. But certainly it indicates the increased focus on all things related to energy. And we're dealing with a wide variety of technologies right now that are, in some cases, very exciting, in some cases pretty dumb, but they gain a lot of public attention. Everything from clean coal sequestration. Can you really pump CO2 into the ground, and will it really stay there if you do? A question for our geologist friends. Is nuclear power coming back? What about all the renewable and alternative energy? Everybody wants to have windmills or photovoltaics, solar power plants. And in fact, some of you probably heard that our brethren in Florida Power and Light, had a massive blackout just the other day. It took out about 1 million customers. And one of the first things a advocate said was, well, if Florida Power and Light had alternative and renewable energy like wind and solar, this wouldn't have happened, which of course is preposterous, because the problem wasn't the supply. The problem was really how you move the supply to the end-use customers. How do you actually get power? Hopefully it's power that's being used efficiently, which is the focus of the Center for Energy Efficiency, but you've still got to get the power there. And ultimately that demands a grid, an infrastructure that in the past has frankly been pretty dumb, hence the term the smart grid. And that's what I'm going to tell you about. Now, one of the things that I've found particularly interesting about the smart grid, as we've looked at it at Southern California Edison, we've obviously got a lot at stake. We're the largest electric utility in California, one of the largest in the country. PG&E used to be larger, but we're now #1 in California, and we don't say that to gloat. Well, maybe a little bit to gloat, but we manage an awful lot of assets for transmission and distribution, and an awful lot of interaction with customers. We've got about 5 million customer meters, and we'll talk about those a little bit because they're, by the way, all being replaced over the next 3 or 4 years with new technology. So the grid is really our province, where we try to worry about how we reliably supply you power in this very rapidly changing world. But we find that smart grid is a cool term right now. Everybody wants to talk about smart grid, and I'm amazed. I received some on my BlackBerry as I was coming in this morning, some advertisements from some consulting firms who I know all these guys, and they're marketing themselves now as experts in the smart grid. They want to have seminars and help us with the smart grid. These are the same folks who were experts in alternative renewable technology a year ago, and a year before that were experts in energy efficiency, and a year before that were experts in diversification. But smart grid's a hot topic. There are at least 14 national initiatives that I've counted that have something like smart grid in their title. They're federally sponsored or state sponsored or industry sponsored. The problem is they're all very provincial. They all go to one little aspect of what a smart electric grid might mean. So at Southern California Edison, in the efforts we've put out, we've tried to take an expansive, inclusive view and said that the smart grid that will serve all of you in the future really goes from the generation all the way to your meter and beyond into your home. And that if we don't capture all of those applications and have a vision for them, then we're missing out. So What is this? Well, a couple of things. One, an advanced grid, I like to say this all the time, especially when I'm with research scientists, an advanced grid that doesn't better serve customers is showmanship, not smart. It's just putting widgets on. And widgets by themselves don't mean a lot to us. What are we going to do to change the relationship we fundamentally have with customers? And here's the secret. We're going to enable, we hope, thousands of what I used to call, by the way, this is the last presentation I will ever use this slide or anything like it. What I actually started using the term a couple of years ago, integrating thousands of IEDs, intelligent electronic devices. The dean's laughing because he got it. I've put this up and I almost got arrested because IEDs now have a different meaning. Improvised explosive devices, right? We've all heard it on the news. I'm really not going to put those in your homes. So we're going to change them now. Even though we were first, we have to call them SEDs, smart electronic devices. The grid of the future is going to have thousands, tens of thousands, ultimately hundreds of thousands of smart electronic devices that are interconnected with high-speed networks to send millions and millions of pieces of data per minute and eventually millions of pieces of data per second, convert it into useful information and enable it to serve customers more reliably, more cost-effectively, and more environmentally efficiently. Okay? That's the vision. And we're part way there, but we have a long way to go, and I'll talk to you a little bit about that. So, the grid of the future will ultimately be largely self-healing. And when we think about many of our telecommunication networks, a little easier challenge with low voltage and so forth, and many of our computer networks, we've seen large advances towards self-healing networks. Networks that can diagnose their own problems and largely fix them before you notice them. If you actually monitor what's happening on your internet, you would find that it's a frequent occurrence to have a particular node of the internet that's serving you go down, but you don't know it. There's a little blip, takes a little longer when you hit the return key, and then you keep computing. Why? Because of this interconnected grid. Now imagine extrapolating the same idea to the electric grid, which fundamentally over the years has been quite dumb. Now why has it been dumb? Well, number one, because it started a long time ago. We put in our first electric facilities 125 years ago. There weren't a lot of computers. In fact, I went to school before computers, and I love to tell a true story. A group of young engineers who worked for me not too long ago, I pulled out this ancient artifact when I addressed all of them, and I held it up, and I said, "This is how I learned." And I said, "Who knows what it is?" Not a hand went up. Of course, many of you know what it was. It was a slide rule, right? My old yellow Picket log slide rule, which I can still crank pretty good on. None of them had seen one before. And I said, they tried to figure out what it was. I said, well, it's basically a computing machine. And they said, oh, go on. Totally baffled them that somebody could actually do computing on that device. So we built this infrastructure over 125 years, and much of Southern California and Central California's infrastructure was built post-World War II. The boom happened and that infrastructure was put in. These assets are fundamentally very long-lived. I have a A-bank transformer operating not too far from here at Bailey Substation, which has been in continuous fully loaded service for 76 years. I have hydroelectric plants in the Sierras that were built and have been in continuous service with only normal maintenance and overhauls since 1911. Now imagine a computing environment where you're using the computer that you had 10 years ago. Remember what computer you had, and can you imagine using it today? So that kind of change is difficult to assimilate in very large capital investments that have very long lives. But we believe that this self-healing smart grid that I'm going to tell you a little more about will ultimately be so powerful, and we have many of the tools right now, that we like to say that if smart grid technology had been fully deployed, the Northeast blackout would not have happened, would have prevented it. And it does it essentially by using modern technology to do the 5 things that I've outlined here. Smart grid identifies a problem, it analyzes it, it isolates it to the smallest possible area, it remediates, that is, it fixes it, and then it reports to humans on what it has done. Right now, the way an electric grid works, for the most part, although we have a lot of automation compared to most utilities, we have the most automated distribution system in the United States at Southern California Edison, with 30,000 automated switching devices already deployed. But right now, fundamentally, the system is smart enough to tell you it's broken, and then you gather data and decide, as a group of human operators, what to do. Flip switches, reconfigure the system. Obviously, where we have to go, if our grid's going to be as smart as the devices that our customers plug into it, is the grid will have to reconfigure itself machine to machine. Because typically the time spans that you need to keep the grid up and running so you don't notice when major events happen are typically 4 or 5 cycles. Now a cycle, how many cycles? In alternating current electricity, 60 cycles per second, right? So you think of increments of 4 or 5 cycles. The system has to receive information which can be several hundred miles away across the interconnected Western grid, reconfigure itself, and then report back on what it's done. Humans can't act that fast. Now, some of the additional things that we'll get out of the smart grid, and I'm going to show you some of the components of it, but the grid becomes more flexible, and this means that you have higher ability to transfer capacity through the high voltage transmission system, the big towers that you see. You can integrate more renewable and intermittent resources, and this is a big one. If you think about that, one of the big challenges we have, particularly in California, right? California is, depending on how you want to look at it, a national and even a world leader in integration of alternative and renewable power, and we are, in that we have a 20% standard that we've got to meet in the next very few years. It's very difficult. 20% of your power's got to be from renewable and alternative resources. There's talk about a 33% goal, and I've even heard a couple of advocates recently talk about, well, why not 50%? Well, the why not 50% is I told, in fact, one of the founders of the National Resources Defense League, I had lunch with him, and he said, how about 50%? I said, no problem, we can do it. Now, you're going to have to tell me which 8 hours of the day you want electric power. Didn't go over real big. Why is this such a challenge? Well, if you think about the fundamental physics behind all this, the electric power business is pretty unique. Imagine, well, I like to cite my wife, Lee. She's a wonderful lady, but the contrast between the technology that she sees and the stuff I deal with in my job sometimes is fun. She was telling me how cool it was that she could go on the internet. She is on a Mac, by the way. She could go on her Mac, and she could go on to Amazon.com, and she could find what she wanted, and she could click the button, and it would automatically debit her account, and 2 days later, her order would be neatly packed at the front door. And she sees this as kind of the pinnacle of all human achievement. I can shop, and 2 days later, it's at my door, right? Now imagine in my business the same sort of an ethic, which is perfectly satisfactory for Amazon.com or Barnes & Noble, that when you walk up to the wall and you flip that switch, that 2 days later, the lights come on. Wouldn't be satisfactory. That's what's so unique about our business. People say, why all this stuff? Because imagine a business where I have to simultaneously match supply and demand 24 hours a day, 365 days a year, right? When you want the power, I have to make it to order because I can't inventory electricity. I can't, in any effective large-scale way today, store it. So I make it when you ask for it, literally changing the output of the system when you flip the switch. And I do that all day, every day. Now imagine integrating into the middle of that things like windmills, which only produce power when the wind blows. Right? So you flip the switch, and you, let's say, how many of you are supportive of renewable and alternative energy? Okay, that's the vast majority. You're progressive people. Now, how about we sign you up and we just have an agreement that if you flip the switch and the wind isn't blowing, your lights won't go on. Is that okay? Most of you wouldn't sign up. Now, there are some people who are really zealots for this stuff, and bless them. I mean, they're real advocates, and they would sign up. They'd say, well, that's the price I have to pay for clean. But most people would not accept that. So I've got to have a way of providing them power when the wind isn't blowing or the sun isn't shining. And right now, for the most part, that means burning fossil fuels. In California, it means natural gas, a lot cleaner than coal. Right? It doesn't mean coal in California because coal isn't allowed in California. It doesn't mean more nuclear in California because nuclear is currently banned by law in California. So it means, for the most part, natural gas. I want to integrate more alternative and renewable resources. One way I do it is with a much smarter grid. How so? Well, for example, if I have massive wind projects spread across the service territory, we serve about 52,000 square miles. The wind might be blowing at one end when it's not at the other. If I can do that matching. Or the neat thing about solar resources is that the sun tends to be shining the brightest when the wind isn't blowing. It's just one of those meteorological phenomena, right? When does the wind not blow, by the way, on the hottest summer days? Right? That's when I tend to have the lowest output from wind, as a general rule. But solar goes up. So if I can take solar and wind, for example, and balance them, I can actually start to smooth the curve and not have to put so much natural gas on top of it. So this ability of a smarter grid to do this dynamic, real-time balancing is really going to be important to achieving any of these goals about greenhouse gas. One of the other things that I think is going to be key in a smart grid is this idea of customer choice and energy self-determination. And boy, this is one of the most exciting things. Southern California Edison over the next 4 years is going to deploy for all of our customers, except for a few very large customers who already have them, the smartest electric meters ever deployed in the world. Now, that's a pretty bold statement. The reason I know they're the smartest is because we went to market and nobody had a device that met all our requirements, so we challenged industry to develop for us, over a course of 18 months, an accelerated research cycle, a new meter that would do more than any meter ever deployed. And we're going to deploy them at a remarkably cost-effective price to every single one of our customers. At our peak, we'll be putting in 5,000 or 6,000 new meters per day throughout our territory until all 5 million are switched out. And what are these new meters? You'll hear about them. You'll get little mailers before they go in at your house. The Smart Connect meter, it's called. This is a meter which is a true computer and communication device on your home that enables two-way communication, not only between the customer and the utility, which is already very powerful. I mean, imagine that we can read your meter remotely, do turn-offs and turn-ons. You say, well, I want to move. Can you transfer my account? We get your data. We turn your meter off and turn the other meter on. You walk in, flip on the lights. You don't have to wait for a serviceman anymore. It's all done over the network. These meters are communicating over a mesh radio network back with our computer where we can gather usage information, we can help you with energy management, but not only that, the computers in your home will be able to communicate with your meter so that I believe in a very short time, because the market's pretty efficient, you'll be going to your local computer store and you'll be buying something like Home Energy Wizard for $19.95. Be like TurboTax. And you'll pop it in your computer and it will ask you a whole series of questions like, what temperature do you like during the day? What do you like at night? Does it matter if the temperature goes up or down during the day when you're at work? What hours do you work? Do you have pets? When do you like your yard lighting to come on? Do you mind if your pool pump runs at night? All of these questions, and the Energy Wizard communicating with your meter will be able to configure your home to maximize or at least satisfy your needs for comfort and security while minimizing your bill and minimizing the resources that you use, the world's resources, in terms of natural gas and all of the other things. And it's going to do that through this communication link between your home and the meter. Incredibly powerful. Now take it one step further. One of the coolest ways that I can integrate more renewable and alternative resources will be what I've coined, now you're going to love this, and my wife kids me about this, the garage of the future. She said, fundamentally, a garage can't be futuristic. It's a dirty place where you keep your tools. Well, we've actually prototyped the garage of the future. Imagine having a small bank of photovoltaic cells on your garage. By themselves, they're not terribly helpful to the grid or to you. But if you tie them in with advanced battery technology that will be built into new homes, battery in a box in the corner, and advanced control systems that communicate with the meter, now imagine the meter telling your home system when power is the most costly because there's such high demand, and switching you over to your stored power that was produced by your photovoltaic system to reduce your bill and, just as important, reduce the need to burn fossil fuels. Boom, automatically. And it can be smart enough because soon you'll all choose to put in, it won't be mandatory by the way, but you'll choose to put in communicating thermostats. So the meter, if you choose, can send a signal to the thermostat and say, we're really in a tough time and we're having to burn a lot of fossil fuels. So thermostat, I'll let you go up 2 degrees. And if every customer in my territory lets me click the thermostat up 2 degrees for an hour, I save an entire fossil fueled power plant having to be started. That's all it takes. So imagine the promise of that. And of course, then we add to it, you're going to have a plug hybrid electric vehicle in your garage, right? Because you're going to be able to cut your fuel costs by half to 2/3 by using the electric grid with no new construction on the electric grid, by the way. Current study says there's enough capacity in the electric grid because we have to meet your peak demand on the hottest summer day. We build enough capacity in that we could serve 80% or 85% of all the vehicles on the road right now with plug hybrid electric power without building one new power plant, because you'd charge them at night and use the capacity we have available, right? And imagine a world where millions of hybrid electric vehicles are plugged in at any given time, at your work, at your home, meaning I now have thousands or millions of tiny power plants I can call on because you have batteries, rather than fire up more fossil fueled power plants. You could work a deal with me to say, I'll credit you every time I draw power out of all those hybrid electric vehicles to avoid burning fossil fuel. Isn't that a cool vision? And we're not very far away. And I've totally blown off all my slides, which I usually do. Another thing that's kind of neat here, improvement in reliability. Smart grid can isolate very effectively to the minimum number of customers when there's a problem. Right now, we tend to do this by brute force. Car hits pole, right? Everyone agrees that's sort of an unavoidable. Car hits pole. And the entire circuit goes down, 2,000 customers, until we go out and repair. Imagine, and I'll show you how it's done, we have a circuit that does it, that I could isolate that to a small fraction of the circuit and supply all the rest of the customers because I have more intelligence on the circuit. And one of the things that's amazing about modern electric grids, you know typically how I first know that your power is out? Any idea what my first indication typically at electric utilities are? Someone calls. The first indication of a power outage tends to be a customer call. And when we get several customer calls, we start to home in on the area, right? Literally. Now imagine the Smart Connect meter where I can poll every customer in real time and know exactly who's out, when they went out, and intelligent electric devices on my transformers, my transmission lines, and so forth that come back to me and tell me precisely where the problem is. It literally can tell me a pole is down and here's the geographic coordinates, and dispatch a truck with the correct repair equipment and the correct skilled employees to that location on their mobile computer in their truck. Yeah. Oh, no, that's a very fair question. How will the intelligent electronic devices? Number of ways. Some of them have redundant supply, some of them have battery. A good number of them are battery powered, so they have at least some time where they can communicate with me without the grid. And some of the newest ones that I've put in have photovoltaic panels powering their little circuits. So we are trying to think of those things. Thank you. Okay, also, this is a big deal. people forget about it. You know, when we think of heroic workers serving our needs, we think of firemen, we think of policemen, and those are heroic workers, absolutely. I can't say anything but good things about them, but electric linemen do very heroic work. I mean, imagine, in order to restore power to your house, climbing 65 feet to the top of a sub-transmission wooden pole that's swaying 2 feet in an 80-mile-an-hour wind while the rain's blowing down, and working with 16,000 volts live, because they do it all the time. Okay, this is a tough business, and it's a fundamentally dangerous business, and people die doing this business, and that's not okay. So one of the things that the smart grid will fundamentally change is the safety of workers by making equipment safer, by giving us signals that equipment is about to fail before it catastrophically fails, so we can isolate it and replace it. Because high voltage equipment can fail in very nasty ways, and we want to know about it before it fails. We want to prevent it from overloading. We want to replace some of the more dangerous old-fashioned technology like oil-filled transformers and oil-filled switches with solid dielectric, no oil. Solid dielectric technology enables you to have transformers, for example, which when they're severely overloaded, don't go up in flames. They don't contain oil that requires hazardous waste cleanup. They're a solid block, and they go poof, and a little red light goes on, and you take them down. Incredibly good ideas for ensuring not only the safety of workers, but members of the general public. Okay, so we're doing all of that stuff, and I'll tell you a little more about it now. But first, people say, well, okay, so this is trendy. You've told us it's trendy, and everybody's jumping on the bandwagon. Why smart grid as a concept now? Were you bored? I mean, did you have to come up with something new? No, there's really a fundamental reason that science and technology people can relate to. We knew in engineering schools around the country about some of the technologies that could enable the smart grid 12 and 15 years ago. I've got a couple of research scientists who have won international awards for their work on something called synchronous phasor measurement, which I'll talk just very briefly about. 15 years ago, they proved it first on the blackboard and then in the laboratory, but we didn't deploy it in a single place. Why? Because we were waiting for this unique time of convergence. The time of convergence is because basically you need 3 legs to hold up this stool. You need these intelligent, or I'll now call them smart electronic devices, relays, switches, transformers. All of the parts of an electrical system have to be smarter. They have to fundamentally go from electromechanical, the old Frankenstein laboratory switch, to digital, right? They are now computers, fundamentally. That part wasn't hard. The parts that we're missing is, A, you had to have a ubiquitous, high-speed, high-bandwidth communication network. Because if they can't talk to each other, they're not smart. And they've got to be able to communicate one to the other and all of them back to central intelligence nodes, or this thing doesn't fly. That has happened. Affordable, high bandwidth, high speed communication virtually everywhere, even in some cases using wireless technology where I can't get fiber. And I have to have high power, affordable computing, because the computational tasks that we face here are awesome. Imagine being able to receive ultimately, right now I get millions of pieces of data per minute as we stand here today that are being processed into useful information. It will be millions of pieces of data per second. So this is a very, very data-intensive exercise. Requires all the latest thinking on embedded networks and processing tools that enable you to do it fast enough. That requires a great deal of computing power. And now you can do it. Where at one time, places like UCSB would have to rent computing space on supercomputers, the very few places that could afford a Cray. Well, I would pretty much bet that I have more computing power sitting on this table than that Cray. That's how fast the advance has been. One of my engineers pointed out to me, I received many years, decades ago, the first personal computer at Southern California Edison, a because I happened to be one of those nerdy kids who knew how to program in machine language and hexadecimal and all those things. So I was supposed to work on this thing. And we went out for lunch the other day, and hopefully all the men here know what very momentous holiday recently passed. What was it? Valentine's Day. Very good. There's 3 guys here who are happily married. All the rest of you are in trouble. Valentine's Day, and I stopped to buy a card for Lee. And I saw this really cool, $4.95 card that when you opened it, it played music. Many of you have bought those, right? And so you open it and it plays this little song and says nice things. And my colleague who was with me said, and he was serious actually when we thought about it, he said, you realize the card has more computing power than that first personal computer that you received at Edison? Absolutely true. Imagine that in that throwaway card. So really, you see the convergence that was required to make the smart grid possible. Let me show you a few components, because we've talked theoretically. We don't have a lot of time, but I want to show you a few of the goodies and widgets that scientists have developed around the country and how we start to integrate them into the smart grid. A lot of words here. A few things I can tell you about is that smart grid goes to the transmission system, the bulk power that we move around the Western grid. Right? We've got essentially 5 super grids throughout the United States. The 4 on the East Coast are all close together and interconnected, and then the 5th one on the West Coast. And we move the power around the West Coast through these high voltage, typically 500,000 volt transmission lines. We've got a lot of technology now where we can actually use tools that were developed in the lab. The biggest one is called synchronous phasor measurement, that enables us to take measurements in real time all around the Western grid and know where problems are before customers can see them and begin to react to them. So we literally can tell when the electric system is being stressed by events. That's why I say this would have prevented the Northeast blackout, because the phase angles actually start to shift. And when we get too far out of phase, the result is that bad things start to happen on the grid. Really esoteric, really powerful technology, which you're going to see deployed probably by federal mandate around the country, because they have realized that this is going to be the key to preventing large-scale regional blackouts, and you're going to see electric utilities being ordered by federal law to deploy phasor technology, which was largely pioneered at Southern California Edison by one of my scientists named Bharat Bhargava. Some of the other stuff here, and I'll touch on a couple. One of them that is really fun to think about is sort of the holy grail of the electric utility business. When you say, what would be the game changer? Whatever business you're in, maybe on those sleepless nights you sit and think about something that either has happened or might happen that would change your business forever. And if you happen to be in the newspaper business, as a friend of mine is, he had a lot of sleepless nights. Because the real question is, with the advent of a ubiquitous internet, will print media live? Will it survive? Will there be newspapers a few years from now? Well, when you think about those game changers, in my business, the game changer is the development of truly practical high-temperature superconductivity. When we say high temperature, that's not university term, which means, still a couple hundred degrees below zero, but higher than it used to be. When I say high temperature superconductivity, I mean room temperature superconductivity, where I could hold up a wire and it superconducts. When I get to superconductivity, then the whole business changes, because now I can store power. Now I have cost-effective mass storage because of superconductivity. So we're playing with superconductivity in the lab. There's some terrific research being done at MIT, especially right now. UCSB has done some, needs to do some more, because superconductivity is really an incredibly promising technology, but we're still 20 or 30 years off in the laboratory before we'll get all of the advantages. Last one on here, which is kind of a fun thing. There are many issues when you try to manage the transmission system that require you to get data that's very hard to get, because fundamentally a lot of the transmission system is designed to be where you can't see it. Right? Nobody wants to have transmission towers in their backyard. Nobody here would volunteer. Right? We've found, even when we say, well, this transmission line's being put in to bring in clean wind power from the Tehachapis, people say, wow, that's great, you should build that. Now build it in the next town. We hear that over and over and over again. We support you 100%. Of course, it can't be in our town. right? So you end up building transmission as much as possible in areas that are fairly remote and inaccessible. And as a result, imagine trying to look at 300 miles of transmission line to see how it's behaving through the middle of the desert. Awesome task. Now we're developing wireless monitoring systems that hang from transmission lines like donuts that feed back to us in real time the loading on the line, the temperature of the line, which is a consequence of loading, the wind speed, the distance of the line from the ground, because the more you load it, the more it sags. And all this data starts to come back from our lines wirelessly on an automated basis, enabling us to change the way we operate the whole transmission system because we don't have to be there to see how it's performing. And substations. Now you remember, substations are an integral link in the electric power system because you can't take power from that 500,000 volt line and plug your stuff at home into it. Well, you could, but it'd be very messy. Not recommended. So we want to get down to house current, to the voltage you use in your home or your business. In order to do that, we have to do a lot of transformation. We step down 500,000 volts, 220,000 volts, all the way down to 16,000 or 12,000 in most neighborhoods, older neighborhoods 4,000, ultimately to 240, ultimately to 120 at your house, right? In order to do that, we've got to have these substations. You have them in your neighborhoods, then you see big ones further out, typically in remote areas, that handle the transformation of power. Those substations, without them, you absolutely can't have power. And we're making them incredibly smarter with the new technology. The vast majority of our substations are now unmanned because computers can do everything we need to do back to a central site. We secure them and we run them with computers. And we're adding new intelligence every day so that they are more self-healing and can tell us what they're doing. And I want to tell you about something closer to home, and that's the distribution circuit. Most of the problems that you experience with, in fact, I'll be bolder than that, virtually all of the problems you experience with power supply to your home, outages, voltage dips, lights flicker, right, have nothing to do with energy supply. As the dean mentioned, there's plenty of supply almost all the time. So this does not mean, except in very rare instances, that a power plant went down, that we couldn't get enough power to serve you. And it doesn't mean that the transmission system failed. Those big wires, they tend to be very reliable. It's almost always what happens in your neighborhood, the neighborhood distribution circuit. Virtually all of your outages are close to home. That's either a failure in the equipment or it's some act of God. Lightning struck a transformer on top of a pole, somebody ran into a pole and knocked it down, a local city worker dug into an underground line. Happens all the time. This is the area where most all outages occur, on the distribution circuit in your neighborhood. So Edison undertook a project with some DOE funding and some university help to put out there in the world the most advanced distribution circuit ever built, and we call it Avanti. All circuits in the electric business have a name. You name them after presidents or states, or some of them have goofy names, cartoon characters, but it's a way of having a taxonomy so you can identify an area because the names are all alike in the same family. Well, this one's called Avanti, which is Italian for moving forward. This is a real circuit. It's serving 1,420 customers as of this morning out of Shandon Substation. That's its neighborhood substation in San Bernardino. No particular reason why it's in San Bernardino other than the fact that was the next one we needed to build and it was about the right size. So we built Avanti to be a test bed for all the latest technologies on a distribution circuit and put them all in one place so we could test them and improve them. And so far the test is going really well. Let me tell you some of the things that are on Avanti, if my nifty animation works. The circuit of the future. It's got several components that are very high-tech and a few that are low-tech. Fault current limiter. Fault current limiter is a really important device, but it's one you wouldn't normally think of. I like to explain it to people this way. Under almost all of your desks in your offices and your homes, you have one of those surge suppressors, right? That strip you plug stuff into. Why do you have one of those? Protect your equipment. Bingo. This is the world's biggest, most expensive one of those. This is a giant surge suppressor. Static Var Compensator. This is essentially a really smart, really big battery, so that when there are problems on the system or variations on the system, this compensates for them. Now, it does a lot more than that, but that's an easy way to think about it. This is important not only because of reliability of your circuit, but because things like static Var compensators enable us to integrate things like that rooftop solar that you'd like to put on and maintain the quality and reliability of your power system, because when the cloud bank rolls over and you start to see a real drop in the system, the static Var compensator can help roll you through it. So this provides a lot of ability to levelize some fundamental electrical properties. Vacuum fault interrupter. We want to deploy a whole bunch of these. There's a couple of key things. It's a relatively small device, and it's a vacuum fault interrupter as opposed to an oil-filled switch. So instead of interrupting with an oil-filled switch that uses a hazardous product and imposes danger, this operates essentially with air pressure, with vacuum. And these are small, and you put them all over the circuit. So now, when they communicate with each other, as I'll show you in a minute, I can isolate the problem, right? That car hit pole. Now, instead of the whole circuit, one part of the circuit says to another part of the circuit, "How you doing?" And he says, "Well, I'm broken." He moves to the next part and says, "How about you?" And that one says, "Well, I'm fine." He says, "Oh, well, now I can isolate by operating switches to only the part that replied that it was broken." That's the whole notion of isolation. And mobile distributed generation. Sometimes the best thing you can do in the summer, for example, when a circuit is highly stressed in your neighborhood, rather than crank up a fossil fuel power plant, is to move some generation right to your circuit. And we've configured Avanti as a plug and play, kind of like the PC. We can plug mobile generation that we can move around the territory, and this could be a fuel cell, this could be hydrogen powered, it could be natural gas powered, so we can move the resource right to the load without having to fire up a central power plant. And this can be clean resources, at least in the future. That's what we hope for. And that's all connected, here's the enabler, with a high-speed, the animation worked, a high-speed data network that enables all these devices to talk one to the other. Without that, none of this works. Now let me show you a relatively low-tech thing that people don't think about. Typically, one of the things that's most conspicuous about the power system in many of your neighborhoods is the poles. And they're wooden poles. And I like to remind our engineers and our scientists, this is the year 2007, and you are fundamentally involved in a business, this was a big speech I gave them, that relies on sticking wooden poles in the ground and asking men to climb them with hooks on their feet. Does that sound like where you ought to be? So my challenge to them was, how do we make that different? Because it just doesn't make sense to have a product that degrades, that has to be treated in some cases with environmentally toxic substance. It gets termites, it gets dry rot, it gets hit by a car and it's destroyed. So we came up with these so-called composite, or I like to call them Lego poles. And we've actually installed 40 of them on the Avanti circuit. They're not made out of wood, they're made out of a high-tech composite. You'll see there's no wiring on the outside of them, as you sometimes see in your neighborhood, because things like ground wires can all run through the middle. Okay? They're hollow, they're light. 2 men can carry a full-length pole to your rear lot line. Doesn't require cranes or any heavy equipment. One of the reasons why they can do that easily is because our poles are sectional and they telescope, so that you can slide one section into another, and make the whole thing into a 12 to 15 foot package, pick it up, carry it on your shoulders, install the bottom, and simply snap the sections together and build the pole you want. Interestingly enough, one other benefit, we found out that typically when a car hits a wood utility distribution pole, the occupants of the car lose. These poles, because of their composite nature, are so light, tends to break the bottom section, and the remaining sections simply hang from the wires. The crew comes, lifts it up in the air, puts a new bottom section in, drops it back down, and you're back in service. So the composite pole has been one of the fun things we've developed. Last couple ideas for you. Smarter worker tools. One of the most fun things I get to do, sometimes at presentations, is wear my Lineman of the Future outfit, where our scientists have tried to take all the tools we can find and incorporate them into what the Lineman of the Future might be wearing out there, the fashionable lineman of the future. So we now have a helmet-mounted video camera that wirelessly transmits back to engineers or scientists who can look at the same thing the lineman is seeing. We have a wearable computer, fully operational XP computer. We have a drop-down fighter pilot type display. Gives you a holographic kind of an image in front of your face. Two-way communication through several different protocols. So now with my Lineman of the Future outfit, which is admittedly a prototype only, I walk towards the pole I'm going to work on, and it tells me what all the equipment on the pole is through its RFID tags. It gives me the maintenance history of everything on the pole, and it flashes up in front of my face. And then it gives me the specs for the job I'm about to do. And it gives me a safety briefing before I do it. And then as I start up the pole, the camera is transmitting back to an expert at headquarters who's telling me what to look out for in that particular installation. I get to the top of the pole, and all I have to do is verbally ask for it, and I see the schematic and the instructions for the replacement job before me. When I remove the faulty piece of equipment and bring it down, it automatically, because it's got RFID tags, removes it from my inventory and puts in its place the name of the new piece of equipment I installed and updates all of our maintenance records. And that technology works today. We just haven't broadly deployed it. It's really fun. So, what's the difference between the kind of work that makes a UCSB a terrific place and the kind of work we do in the industrial sector? This is really the difference. My motto is adapt and adopt. I don't create much of anything. Creation happens places like this. That's what universities and research laboratories are for. I take the best stuff I can from places like UCSB and steal it as quickly as I can. Now, when I say steal, I pay for it and I do all the proper things. But I want to take the best innovations from the research world and other industries and adapt them to my world, not create them fresh. And I want to as often as I can, adopt things that have been proven in other forums, because I can't afford to take a whole lot of risks with your power supply. I really, if you buy a new computer from Dell or Sony or Apple, and it's got a bug in it, and who hasn't bought a computer that had a bug? In fact, who hasn't bought an operating system, I can't say any specific manufacturer's name, Vista, that didn't work when you first got it, right? Everybody's been there. I can't do that, because if I deploy stuff on the electric system that turns out to have not been a well thought out idea, all of you pay. So this is our credo, adapt and adopt. And here's just the last idea. When does the grid finally get smart enough? Because you're going to hear more and more about this. And of course the answer is no. And fundamentally the no is because we're going through this dramatic paradigm shift, where the grid is going from something which is fundamentally about switches and wires to something which is fundamentally about computers. We're going from an electromechanical age to a digital age. And I like to say, for the geeky folks among you like me, the engineering types, that we're going from Ohm's law to Moore's law. And that's scary, because now we're going to be replacing a system that fundamentally was built to last for each component at least 30 years, minimum acceptable lifespan, and typically 40, 50, 60, 70-year lifespans for equipment, replacing those with computers where I know the lifespan can't be more than 6, 7, 8 years before the technology and the protocols have changed. How are we going to morph an electrical system? So as I like to say, as I started off by saying, it's going to be as smart as the stuff that all of you are going to plug into it. That's our challenge. We thank you for your attention. I went a little long. I hope it was worth it, and we'll take a few questions.